Hello, students. Well, today we're going to discuss Chapter 18, which involves entropy and Gibbs free energy, randomness and spontaneity. It's kind of me to a T, but as we'll see in the next couple videos, we're going to start by looking at entropy and what does that mean in terms of energy. Then we'll look at things such as Gibbs free energy, which is our spontaneity of a reaction. And then we'll look at relating that to some of the previous chapters. So let's go ahead and get started. This video will be all about entropy. So, a couple things we need to remember from last semester has to do largely with the fact we could quantify the energy of a system as the internal energy, and that was largely a function of work and heat. There were some other energies involved, but we neglected them as if it wasn't electrical in nature, it didn't produce energy. If it wasn't big in nature, it didn't have kinetic energy. It didn't have electrical energy. If it wasn't big in nature, it didn't have very much kinetic energy. So there's a lot of energies we could neglect. We talked about the idea of system and surroundings. The heat flows from this place to that place. We looked at enthalpy of reactions, which was the heat flow under a constant pressure system, and we calculated that through the sum of the heat of formations of products minus the sum of the heat of formations of reactants. So those are some formulas you might want to review, some concepts you might want to review if they don't sound familiar to you. So the first law of thermodynamics that we discussed was that energy must be conserved, that energy can neither be created nor destroyed. So the heat lost must go to the surroundings. The heat gained must come from the surroundings. Work is done from system to surroundings, or work is done upon from surroundings to system. But just because energy must be conserved, this doesn't tell us whether reaction will naturally occur. So one of the concepts, we may have kinetic values, we may have equilibrium values, but they don't give a good judge on whether a process would be considered spontaneous, something that will occur naturally without any outside intervention. So some things are more spontaneous than others, like a fire or a spark hitting a very flammable substance will very rapidly explode. But certain things need a lot of energy to make it go. So just some simple non-science ones, like if you put a rock on a steep hill, gravity obviously is applying a force, but you might not need a push. You might not need any force to have the stone roll down the hill. Now, if you put some sort of block or wedge or something to keep it from rolling, you're essentially putting a small little activation energy barrier. But a little natural movement might cause it to roll down the hill. But the idea is a process is spontaneous when it doesn't require really any outside action. If you allow something to mix together, most things will mix over time. Some are faster than others. So you pour cream with your coffee. Yes, you can stir it to mix it up, but it should hypothetically mix given enough time. All gases mixing process is spontaneous. Now, some of these processes are dependent upon thermal energy, temperature. So, like freezing or melting. Below zero, water will spontaneously freeze. If you have water in an area there that's below zero, it will start to freeze. It doesn't need to be windy, it will slowly start to freeze. Above zero, ice will start to melt. You don't need extra solar energy, but if it's above zero, it will start to melt. Above 100, liquid water will boil. Below 100, it won't. So we say spontaneous. It depends upon temperature. So, when we say something is spontaneous, we can also consider the reverse process. That while it may be possible to put things back to where they were, it is often difficult to do without outside intervention, without the surroundings directly acting upon the system. So anything that needs an outside intervention would be considered non-spontaneous. We can move the stone back up the hill, but it requires work. We can use a centrifuge or high temperatures. You can do boiling water back to separate cream based on the density of the liquids or the boiling point. It's not really easy to remove a smell. I guess if the smell is created by volatile particles, you can try to capture said particles. You could flush the air out and get fresh air. That's the probably easiest way. You could probably even maybe condense things out or let things settle depending on what the particles are, what's causing the smell. But so it's not super easy to do. The idea there is that a non-spontaneous process will not occur without an external source of energy. That we've calculated, for example, with Hess's law, certain reactions that would physically not really work very well. You might be able to find a way to make them work, but it's not something that would naturally occur on its own without some sort of energy or catalyst or enzyme, something that would make it work on its own. So with that in mind, we have the second law of thermodynamics that says that any spontaneous process will always result in a net increase in entropy of the universe. Entropy is a new unit we're going to introduce, which is capital S. Capital S for our entropy. Entropy is a measure of the degree of randomness or disorder within a system. So, degree of randomness or disorder within a system. It's kind of, for the most part, can be a probabilistic approach. The idea is it's much easier to create disorder than it is to create order within a system. That gases will naturally want to be mixed up, as opposed to they're going to align themselves based on the atomic weight. They will be, there is some degree, especially if there's certain gases that are lighter than others, but naturally there's still going to be some mixing. An increase in entropy includes such things as changing phases, especially moving more towards the other phases. So solid to liquid, it's typically more disordered because you got a definite shape. Liquid is indefinite shape. Liquid to a gas. Now you no longer have a definite shape. You don't have a definite shape, and you don't have a definite volume. So indefinite shape, indefinite volume, very disordered, and able to move in a wider range of places. Anytime we increase in temperature, we're almost always going to see a change in entropy, because things vibrate based on temperature, and so when they vibrate, they can vibrate more. They can move around more. And so you're going to see the temperature going up, and that's going to increase the entropy. Most times, a dissolution from a solid into solution is going to increase the entropy, but it doesn't always. And that has to do with interactions with the salt and the water. If the water has to cluster around and hydrate the salts a lot, you can lose entropy because the water now is stuck hydrating the salts. But generally, a mixing of different things usually increases entropy. Most mixtures are going to be higher in entropy. So alloys are more entropic. Any mixture of gases are more entropic than just by themselves. And an increase, anytime we increase the number of particles, you usually see an increase of entropy. So more atoms in a system is going to increase the entropy. You have more different possibilities of how they are going to be located. Now, in terms of chemistry, and the entropy is randomness. In terms on a molecular level, we can understand it probabilistically that a molecule is acting in a certain way in a certain place at a certain time. So given a quick snapshot, you can look at think of a multi-universe approach of each molecule has a set limitation of where it can be and what type of movement it can be doing. If we look at all the possibilities, we're looking at the total number of entropic states. So it can be moving various translational states, especially if it's a gas. It can move up, down, left, right, front, back. It can be vibrating, where the bonds are going to be stretching and bending and twisting, like the molecules doing yoga or stretching its joints. And the different atoms can be rotating, spinning along their bonds, or just overall just spinning. Like, imagine like a spaceman in 0G doing like either grabbing the wall and then spinning like 360 degrees around, like a front spin or side spins. And so the molecule can be spinning like that, or the bonds themselves can be spinning and twisting, as long as there's single bonds. Basically, all of these possibilities, most of them are energetically equivalent arrangements called microstates. The microstates, we're going to use the term W there. We're not going to really need to do this because I'm never going to test you for this. But the idea is, these microstates, if you calculated all the possible microstates, you could directly correlate them to the entropy of a molecule by taking the Boltzmann's constant, which is essentially just the gas law constant divided by Avogadro's number, but the Boltzmann's constant times the natural log of the number of microstates, and that would be the entropy of that molecule. One of the big things here is, unlike enthalpy, entropy has a calculable 0 point. Entropy has a absolute entropy that is calculable. Enthalpy, with the H, is impossible because we're measuring the change. There is no thing that is said to have zero enthalpy. And we have only given an artificial enthalpy based on the definition. So this brings us to the third law of thermodynamics, which helps us out. That they say the entropy of a pure crystalline solid at 0 degrees Kelvin is 0 joules per mole Kelvin. So entropy has an absolute 0. So, because the idea is that at 0 degrees Kelvin, all molecular motion stops. If it's a pure, ordered crystalline solid, there's only one possible microstate for this pure crystalline solid, and it's not moving, and so you have the natural log of 1, which is just 0. So it's possible to calculate an absolute entropy. So all compounds and all pure elements will have some small entropy value. But we can still calculate a delta S of a reaction by just saying the sum of all the entropy of products minus the sum of all the entropy of reactants. But please note that when done at standard state conditions, assuming all things are 1 molar, 1 atmosphere, and it's done at 298 Kelvin, we can get the entropy, change in entropy standard. Or not. Say delta S naught. That's not like, not NOT, but the naught. Like, so this can be calculated similar to delta H naught of the reaction, except that there's almost no zero values in these calculations. There's maybe one zero value that we have to do, but everything else has a real entropy value. Now, so let's do a quick calculation for these. We have N2O4 goes to 2NO2, and 2O4 goes to NO2. Let's say 304.4 and 240.1. And then we have zinc plus 2H plus goes to zinc 2 plus and H2. The only true zero, this is the only artificial zero we set, is H plus, and that's because H plus you can't have a cation without an anion. And because you cannot have a cation without an anion, you can't get a cation just by itself. And so, with that in mind, we set H plus to be 0 so we can measure all anions based on the cation. And then, so you could use H plus to get chloride, and then you could get chloride to get zinc, or chloride to get sodium, and you figure out everything else after that. So our delta S is going to be our S products minus our S reactants. Our products, 240.1, but there are 2 of them. And our reactants is 304.14. $240.1 times 2 minus 304.14. The entropy of this reaction is 176.06. That's joules per mole Kelvin. Joules per mole Kelvin. Saying that this is an energy that is much smaller than our enthalpy, so it's joules per mole instead of kilojoules. And it's also temperature dependent. So in this case, our products, for the next guy, our products are 130.7 and negative 112.1 minus, in this case, 41.63 plus 0 times 2. Now, there is also going to be very few negative entropy values. The reason why there's any negative entropy values has to do with zinc 2 plus not liking to be in solution. That zinc 2 plus, when it dissolves, has to be hydrated by a bunch of waters. And because there's less water being water, the entropy of the system goes down. So there's my products, and I'm going to subtract my reactants. So entropically, this system loses entropy for this to happen. This loses entropy for this to happen. That when I mix an acid with zinc, it dissolves and forms hydrogen gas, but it loses entropy when it does that. But this reaction still occurs. This reaction still occurs. Oh, I wrote that down. 304.4. Yeah, well, it's close enough. This reaction still occurs because of enthalpy, and we'll talk about that more in a second. So, delta S of our reaction is essentially delta S of the system, because we're going to study typically a given reaction, and that's going to be the system that we're studying. So the entropy of everything else would be considered the surroundings. So with a spontaneous process, if we add up the entropy of the system and the entropy of the surroundings, those together would be the entropy of the universe. And the second law states that the entropy of the universe must always be positive for a spontaneous process. So, with enthalpy, the system had very little effect on the overall energy in the surroundings, because overall the temperature does not change too much, but we don't change the overall temperature of the surroundings. However, heat flow to the surroundings does increase entropy. A campfire, you're not going to heat up the entire forest by having one little campfire on a cool night, but it does warm up the air nearby. It does change the entropy in the surroundings as a whole. So this process is going to be considered isothermal, which means even though the overall temperature does not change, we see heat flowing to the surroundings. Now, because heat flows to the surroundings, we're going to see a negative Q. Now, because entropy is temperature dependent, we need to include the temperature of the surroundings to figure out how big of effect this is. Because if you're throwing a little bit of heat energy when the temperature is low, it's a lot of energy and it has a big effect. But if you throw in a little bit of energy in when the heat is high, when the temperature is high, it's not going to have a big effect. You give $100 to a college student, they're going to have a good day. You give $100 to like Elon Musk, he's not going to really care. I mean, maybe it's like, oh, that's nice, but like he has enough money that $100 isn't going to change his day in any way that's going to be super important. So we can look at the enthalpy or the entropy of the surroundings as delta H of the system. We make it negative over T. So the surroundings are acquiring kinetic energy from that heat, and this will disperse. And so we're calculating the entropy of the surroundings. So with that in mind, let's calculate the entropy of the universe for the following system at 10 degrees C. So T is 10 C, and we have silver nitrate and sodium chloride goes to silver chloride and NaNO3. And I'm going to write these guys down. So H, S. 100.7, and we have 220.37. NiCl is 7.1 and 115.5. Negative 127, 6.11, and negative 446.2, and then 207. Okay, I need to write these down real quick just so that when I go to the document camera, I don't have to come back to this right away. Okay, so let's calculate the delta S of the universe. Is going to be delta S of the system plus the delta S of the surroundings. And so the first thing is, what is the delta S of the system? It's going to be just products minus reactants. So products 96.11 and 207.0 minus 220.37 and 115.5. We know this reaction occurs because when we studied our K expressions, we saw that the K was really small. And we know when we mix sodium chloride with silver nitrate, it forms a white solid. So we know this is spontaneous, but by delta S alone says, no, this should not be spontaneous. It's a loss of entropy. But the delta H of the system, let's look at this. Delta H of the system, negative 127, negative 446.2, negative 100.7, and negative 407.1. Negative, just make all those signs positive. So, that in mind, negative 127 plus negative 446.2 plus 100.7 plus 407.1. And you get negative 65.4 kilojoules per mole. So delta S of the surroundings is going to be negative of a negative 65.4 times 1,000 to get this into joules. And we got to divide by my temperature in Kelvin. So 10 degrees, so we add 273 onto that, so that becomes 283. So, times 1,000 times negative 1 divided by 283, and we get the delta S of the surroundings is 231.1. We'll say 231.1. So, when we add this all up, negative 32.8 plus 231.1 all said and done, the entropy of the universe goes up by 198.3 joules per mole Kelvin. I know it's a hot mess. But here's the work again. So we calculate our delta H, we calculate our delta S, calculate the S of this universe, the S of the surroundings, and then add that to the S of the universe. And that, we have 198.3. So this is spontaneous. It fulfills the second law of thermodynamics, that any spontaneous process will naturally occur and increase the entropy of the universe. That's where I'm going to have to stop for this video. In the next video, we'll look at Gibbs free energy.